and it is really a pleasure to introduce Alberto Loarte. Alberto Loarte is the head of the science division of ITER organization. So Alberto is right in the middle of everything that's going on in ITER. So when you see that there is something going on in ITER, there is new plans, there is a change of the walls, then you have to picture Alberto sitting down in his desk thinking, how is this thing going to work out and how are we going to do it? So we are really happy to have him here also because Alberto, despite of being really busy, he's always been a supporter of fusion activities and also a support of involving students in research and in showing the activities of ITER to students. So thank you very much, Alberto, for being here once again with us. And yeah, please go ahead. The floor is yours.
Okay, thank you very much. So in this along the last theme that you said, in the ITER organization, we have internship for master students. They should have come out at the end of this year, but because we are making plans, will come next year. But you know, if you are interested in doing a research project, typically 6 months, 4 months to 1 year, at the master level, as part of your master project, please check the ITER webpage, which is iter.org, early next year, because there will be a list of projects. Many of them, not all of them, but I would say probably more than 50% are done in the science division. So we typically have a good population of master students. At the moment, we have 6. So actually 20% of our staff at the moment are master students. So we have an active an active campaign in this, and we welcome in general, the experience we have is very good. And we get, some of not all of the master students do, but some of the master students get publications from what they do as members of the paper, and some exceptions, there are not many, but I would say 10% actually publish a paper themselves out of the work they are doing with us at ITER. So if you are interested, please keep looking at the webpage at the beginning of next year. I think will be mid-January, from mid to end of January, the project will come out. Okay, so now I'm going to give you a brief overview of, a moment, I have to share the screen, of what is the purpose of ITER and also where we are, because as Dario said, we have done plans, and there are changes of plans I have to get rid. Sorry, I'm trying to get rid of the window. Okay, now. So the talk is called Objective Status of the ITER Project, which is the first fusion reactor under construction. So what I'm going to do in this talk is to give an overview of what are the ITER mission, what are the bases, the goals, what are the scenarios we want to demonstrate, and the overall design, then update you on the ITER project and the overview of the construction status. This is a short summary of what we have done, and particularly of the problems we have found. And then what we are doing to minimize the impact of these problems that we found, but also to try to maximize when you have a equation, you have an equation, but the equation has solutions depending on the boundary conditions. Now, when our boundary conditions have changed, and what we are trying is to find the optimum solution with the new boundary conditions. And this requires some changes of some things that have been part of ITER already for many, many years, and because the evolution of science, this is a good time to adjust and tune to have a better chance at demonstrating the project goals. So the mission. So the mission of ITER is to demonstrate the scientific and technical legal feasibility of fusion power as energy source. So it is a project which has two goals. One is to demonstrate the scientific part of fusion, but also the technological part of fusion. Of course, some things of fusion cannot be demonstrated at ITER, like the damage to the materials and the high neutron fluxes, but otherwise we demonstrate most of the technology that you need for a fusion reactor. This is done through the deuterium-tritium fusion reaction, which produces an alpha particle and a neutron. The neutron, of course, goes to the reactor walls, and the alpha particle is contained in the plasma. This reaction is chosen because at the temperatures that we can achieve on Earth, In fusion devices, this is the one with the highest reactivity. Typically, it's 100 times higher than the DD ratio or the helium-3. And so ITER operates typically in the central temperatures of the order of 30 kiloelectron volts, which actually is 150 to 300 million degrees Kelvin. So in order to produce net fusion energy, what you need to get is that the reaction of fusion, the energy that produces, which is the alpha particle and the neutron, actually produces more energy than the energy that you need to get the gas to get to these high temperatures. So we characterize the efficiency of this production by the what we call the Q, again the fusion amplification factor, which is the ratio of these two. And so as you typically here, ITER, and I will mention it, is designed to produce 10 times the energy that you use to heat up the plasma. And this is, of course, a round number is 10, and it's very easy to communicate. But actually, the reason why it's 10 is not because it's a nice number to communicate. There is a very profound physics reason. And the reason is that when you produce fusion power, as I said, the alpha particle that you produce from the DT reaction is produced at rather high energy, at 3.5 megaelectron volts, and collides with the other nuclei, the deuterium and the tritium nuclei, which are in the gas, in the plasma. And so the total net heat to the plasma is the sum of the alpha particles and the external heat you put. And ITER aims to demonstrate that the plasmas can be dominated by the self-heating. So it's a system by which most of the heating that you need to maintain the reaction comes on the reaction itself. And therefore, you first get very large amplification factors, but also it's a self-control process. And this is something which we cannot achieve into the experiment. Into the experiment, the energy which is produced by the reaction, like this P alpha, is typically much smaller than the one we used for external heat. For instance, in the jet experiments, the total fusion reaction power is of the order of 12 megawatts, of which about 1/5 is the fusion power. So we are talking of 2 to 3 megawatts of alpha heating, and they use 32 megawatts to heat the plasma. So actually the amount of the energy that the plasma produces itself to self-heat, not the one that goes in the neutron, is negligible. In the case of ITER, we want this to be dominant, and dominant was decided to be characterized by the fact that the alpha heating has to be twice the external heat. Because the mass of the neutron is 1/5 of the total, so the helium plus neutron has 5 atomic masses in total. This means that the helium takes only about 1/5 of the energy. And therefore, when you have a fusion amplification factor of 10, you get that the ratio of the alpha heating to the external heat is 2. And this is what is important from the physics point of view. You have a plasma which produces actually 2/3 of the heated power comes from the reaction, and therefore is relevant to a fusion reactor, where this has to be typically, not like in the case of ITER, which is a factor of 2, higher, it should be probably a factor of 20 higher. Typical fusion reactor designs work with a fusion amplification factor of the order of 30, 40, so it has to be many times that what we have in ITER. So we are talking of, I said, 8 times, 10 times, 5 times, something like that. Now, of course, obviously, when you heat up a plasma to such very high temperature, the gas is ionized, so the electrons are not anymore bound to the nuclei, and this is what we call a plasma. This cannot be contained in a material, because if it hits the walls of any vessel, it will transfer all the energy to the wall, and therefore we have to contain this with the magnetic fields. We can use then the properties of the charged particles, so particularly the Lorentz force, which makes the ionized particles to follow the magnetic field lines, and then we can put this gas encaged into a bottle, which is what we call magnetic confinement. And these magnetic fields that we create, and there are several ways to create these magnetic fields, one of which is what we call a tokamak, which is the design of ITER, are used, these magnetic fields are used for 2 functions. One is to reduce the heat losses across the magnetic field, because the particles have to follow the field line, and therefore they cannot go freely to the wall and lose the energy. Therefore, we contain the energy and we maintain the energy in the gas, so that when the energy is produced, it stays these alpha particles remain in the gas and can transfer the energy to the other ions. But also because when you have a hot gas, the gas expands, and you have to provide the compression force. And the compression force is provided by the magnetic fields, by Ampere's law. So if you induce a current into a gas, the current tries to attract over itself, and this gives you the compression force to resist the expansion force. So the design of what is ITER, these magnetic fields are made by a set of coils. There are 3 sets of coils which are very important. You will see them later. But one is what we call the toroidal field coils. These are these blue, let me put the laser pointer. These are the blue coils which go around the plasma, and they create a magnetic field in this direction, in the toroidal direction. So this, of course, a torus. Then you have a central solenoid, which is the green coil in the middle, which induce a current in this ionized gas. So this is like a transformer in which one of the sides of the transformers has many turns, and the other one has a single turn, which is the plasma. So here we induce currents of many millions of amperes. And then to control the shape and the position of this plasma, we have these gray coils, which are what we call the poloidal field coils, that actually allow us to control the shape of the plasma and also its position. This is very important so the plasma doesn't go against the wall of the reactor, and also because the shape of the plasma determines how much pressure the plasma can sustain. And this is important because, as I will describe later, the amount of fusion power that you can produce depends on the plasma pressure. You have all these currents and fields have to be in specific ratios, because if you have too much current in the plasma, it becomes unstable and actually loses, the magnetic field structure is lost. And this is what we call the safety factor in tokamak, which is small q, and it's characterized by the fact that if you have are the field lines go in the toroidal direction, they also go around in the poloidal direction. And if you make less than 2 turns in the long direction, when you do 1 turn in the short direction, actually the plasma is unstable. So this provides limits to the magnitude of the current, the size of the plasma, etc., which are actually used for the design of ITER, as I will explain later. Now, in principle, because you have a current in the gas heats up. This is like a neon bulb. When you circulate a current, you actually see that the gas emits light and it gets hotter. But the plasmas have a property which is unlike solid matter. Normally, when you increase the temperature of a material, the electrical and the thermal resistivity go up. This is because when the electrons try to go up the material, because the thermal oscillations of the electrons in the material increase the collisionality, it is more difficult for materials to conduct electrons and conduct heat, due to the fact that the atoms and the electrons are moving, and therefore they interact more, and the diffusion of the current along the material slows down. In the case of plasmas, it is the other way around. The faster the particles are traveling the plasma, so the hotter is the plasma, the less is the probability that they collide with each other. This is due to the fact that the interactions are from Coulomb's law. And so the hotter the plasma it is, the less resistive it is, and the more difficult is to heat it up. And this means that if just by conducting current into the plasma, you cannot heat up the gas to very high temperatures. Typically, you are limited at temperatures of few tens of millions of degrees, and this is insufficient for the diffusion because you have to get to hundreds of millions of degrees. And you cannot increase the current more, because apart that is very inefficient, you have this limit that then you do too few toroidal turns and the plasma becomes unstable. And so what we do to heat up this plasma, we use 2 types of heating schemes. One is we couple radio frequency waves. So this is a very similar principle to the microwave oven. Of course, we do not resonate on the frequency of water. We resonate on natural frequencies of the electrons and the ions going in the magnetic field. So this is what is called the cyclotron frequency. And another way to heat up the plasma is we introduce very high energy ions. So we accelerate deuterium nuclei to typical energies of 1 mega electron volt, and then we inject it into the plasma. And by collisions, they thermalize and they increase the plasma temperature. So this is like if you want to heat up water, you can take a small amount of water, make it boil, and then put it in cold water, and then the temperature of the mixture goes up. Because of course these ions would be trapped in the magnetic field as soon as they enter the torus. Actually, they have to be ionized, they have to be neutralized first. So that is why we call it neutral beam injector. These are very large accelerators that produce amps of currents. So they are unlike, let's say, typical particle accelerators where you produce very high energy and very low current. Here we produce very high current and not so much high energy. It's 1 mega electron volt, which is it's not tera electron volts, but the current is, as I said, is tenths of amps. And you inject these energetic ions, then when they enter the hot gas, they are ionized, and then they deposit the energy. And these are the two schemes that we have to heat up, to go from plasma temperatures of 10 millions of degrees to hundreds of millions of degrees, which we need for fusion to take off. Now, with this, you can actually design a tokamak. The thing that you need to understand is how much energy you want to produce. This tells you how much pressure you need to keep into the plasma. And from this, an empirical scaling laws, you can actually design a machine. So ITER is designed on an empirical scaling, which is called the ITER HMOT scaling, and I will explain later what an HMOT is, in which you can actually what you do is you determine how long the energy stays in the gas, and this is related to the dimensions of the tokamak that you are building, is related to the magnetic field, the plasma current, etc. And this is based on empirical scaling. And on the basis of this, you can design what is the plasma current, what is the size of the tokamak, how much power you need, what is the magnetic field you need, and what is the current, taking into account this stability. As I said, the value that we took as maximum possible stability of this small q is 2. This is, of course, the maximum limit, so therefore ITER is away from that limit, is designed to a value of 3. So this means that the maximum plasma current that we can create in it is such that when you go around the torus, following the field line, you do 3 toroidal turns per poloidal turn. So 3 turns in the long direction compared to turns in the small direction. And what you see is that as you want to get more and more fusion power, the machine has to be larger and larger and larger. And this is something which is, I would say, not unique of fusion. This also happens in nature. So here you can see, for instance, the weight and bit rate of various animals. And what you see is that if you want to basically, with a small amount of energy, or a relatively small amount of energy, get the animal to stay alive, and this means you have to have with a sufficiently low heartbeat rate, the animal has to be large. And this is due to the fact that the losses of the heat of an animal goes as the ratio of the volume over surface. So the less you get less losses, because you lose the heat across the surface, you get less losses the larger the animal is. In fusion plasmas is more or less the same, but the quantity that decreases the losses is not just the radius, is the product of the radius and the magnetic field. So if you maintain this value large, you can reduce the losses. And this is why there are some approaches that I'm sure you have seen, which is a similar approach to ITER, but using superconducting coils that can go to higher field. And then you can play the field, the magnetic field value. ITER has a magnetic field of 5 Tesla. If you go to 10 Tesla, you can make a machine which is twice small, because the product is of toroidal field and radius is what controls the heat losses from the plasma and the energy you can produce. Now, ITER as such, I said, it is aims to demonstrate these scientific goals. What it is a very large tokamak. You can see here, this is the size of ITER. In red is the size of a person. So this is about 30 meters tall. The gas has a volume of about a bit less than 1,000 cubic meters. And the way we want to run the machine to demonstrate these scientific and physics goals are explained here. So we have several ways to run the machine. which are what we call our reference scenarios for fusion power production, what we call inductive scenario, in which we run at the highest plasma current and magnetic field, which is 15 megaamp in the plasma and 5.3 Tesla in the center of the chamber. With this one, we produce this gain of factor of 10, which means that the alpha heating is twice larger than the external heat. And this, since it is a transformer effect, we can keep it running for the order of 300 to 500 seconds. So we are talking of 5 to 10 minutes. Then we have other scenarios which are more attractive from the point of view of fusion reactors because they can be kept longer, but they require specific plasma parameters and characteristics that we believe that we can achieve in ITER, but we are not 100% sure, let's say, compared to the first one. And these produce pulses which are much longer, potentially stationary, completely stationary, durations of 1 hour in ITER. This is limited by the amount of heat we can reject to the atmosphere, not because of any limitation of the machine itself. But for this, we only expect to be able to demonstrate a fusion gain of 5, which means that the alpha heating in these regimes will be similar to the external heat. Now, what does it look? What does it look when I say this Q equal 10? Oh, this thing doesn't play. A moment. Sorry. So what does it mean? This? Okay, so this is a typical discharge in ITER. You create the magnetic fields. The red trace is the plasma current. You increase the plasma current. You put some heat in the plasma. Then you increase the density, and at some point around that time, actually, a bit less than that time, you actually see that the plasma temperature starts to be sufficiently high for the alpha heating to take off. This happens typically of the order of 70 seconds. Then this is maintained up to about 500 seconds. You see that by this time, the coils in the center of the machine are getting red. This means that they are reaching their maximum plasma current. And at some point, because of this, you have to stop the discharge and you have to ramp down. So you have to land. And this is a typical plasma discharge. This is very similar to what we do into the experiment, with the exception that, of course, in ITER, because the very large size and the plasma will be very hot, and then we will have alpha heating. Present experiments have the same as this, simply they do not have alpha heating. And you just put the power, you see the energy of the plasma going up, you don't have enough temperature to get fusion power, and then you land the discharge. And the main difference in ITER is this. Of course, this makes the plasma completely different because, as I said, it's heated by itself, and therefore it poses many challenges to the sustainment and the control of these characteristics. And this is what we want to demonstrate in ITER, because this is what you need to make a fusion into an energy source. We also have other regimes. As I said, the one that we have that is the longest is a 1 hour pulse. The main interesting part of this type of plasmas is that actually the plasma current is not anymore driven by the central solenoid. The plasma current is driven by processes in the plasma due to transport, which are called the bootstrap processes. This is due to the trajectories of the ions and the electrons in the magnetic field, and also by external means. So you can see on the right side the profile of the total plasma current in the plasma, where 0 is the center and 1 is the edge, and you can see the various components. So the total is the red, and these components are divided between the current, which is driven by these hot neutrals which are injected, because when they are ionized, they of course go in a particular direction, and they are ions and therefore carry current with them. And also with some of the radio frequency heating, which is the electron ones, because when you launch the waves, you accelerate the electrons more in one direction than in the other, and this creates a current. And the blue one is, as I said, this is the self-driven current into the plasma because of its high pressure. And when you add all of them, you get the red trace. And this means that there is no effect of the central solenoid. So this discharge is not sustained by a transformer effect, but by the plasma itself and the heating schemes, and can be maintained indefinitely. The main complication of this type of regimes, as I will say later, is that you have to get to very high plasma pressures, and this is very difficult. And this is one of the aims that we have to demonstrate in ITER, but we are not sure to which level we will be able to demonstrate it or not. So now, how do we achieve this plasma energy? So this is typically when you have a plasma in a tokamak or an accelerator and in a confinement bed, you have three types of pressure profiles. One is what we call the L mode, or low energy confinement. This is the first results that were obtained in the tokamaks since their birth until the early 80s, in which you, of course, have the center of the plasma has higher pressure, higher density, higher temperature, and towards GS you have a rather low values. Now, this is not viable for a fusion reactor because the total pressure that you have there is rather low, and the energy and the fusion power goes with the plasma pressure square or the plasma energy square, once the temperature in the center becomes about more than 100 million C. Then in the 80s, in the early 80s, a spontaneous transition was found out, which is what is called the high confinement. This more or less doubles the plasma energy, and what it does, it creates a very large pressure gradient and temperature gradient at the edge of the plasma. And the physics of this is not yet understood in detail. I mean, we understand many things, but quantitatively not. And what it does is just this reduces the overall energy losses from the plasmas and increases your energy by about a factor of 2. So we use this as a reference value, and this is why this H factor, which is like the normalized energy confinement that you get, is 1 for this regime. And this is the basis for the design of ITER for this Q equal 10 scenario. Afterwards, this was more in the late 90s and the 2000s. This regime, as I will show, has specific features because here you have very, very large pressure gradients at the edge that trigger instabilities that have to be controlled. And I will describe this in the next slide. But as I said, in the 90s and the end of the 90s and the 2000, beyond there were regimes in which was found that not only you have this reduced transport in the edge of the plasma, you can also get reduced transport in the core of the plasma. And this is what is called the improved high energy confinement. And this is on what is based the ITER scenarios when we make long pulse, so these Q equal 5 scenarios, and the physics of how this extrapolates, well, the physics of how, let's say, the H mode extrapolates to fusion reactors is quite clear. The physics of how this improved high confinement regime extrapolates to ITER is much less clear. And the reason is that we are not 100% sure what is the key parameter that drives this. It can be the presence of very fast ions, which in that case, it is very favorable for ITER because in ITER, these very hot ions that we inject are very fast, and also the alpha particles are produced at very high energy. It could be due to the fact that the plasma rotates very fast. This doesn't extrapolate so well because these fast ions that we inject to heat up the plasma actually don't push the plasma so effectively, while in present experiments, lower energy ions are injected and they push the plasma faster. And depending on what is the dominant mechanism that actually leads to this improved confinement, what we will see in ITER will be one or other thing. And this is something which is the role of investigation of ITER itself. Now, as I said, these very high pressures that we see at the edge trigger instabilities. This is what called ELMs. And actually, this is a tradition in Eindhoven University, the modeling of this. And we have to control them because the energy that they put on the wall is significant. And we can actually melt the wall and the divertor of ITER. Other thing is that the energy that the plasma loses is deposited in very small areas. And they can also lead to very high temperature and melting of the divertor. And because of this, we have to inject impurities in the plasma and radiate the plasma energy away. So not only we have to get a good confinement of the plasma and very high energy and temperature at the core of ITER, but we also have to get low power fluxes to the wall, because if not, we have the risk of damaging the wall. And finally, one of the things we have to avoid in ITER is to have global instabilities. These global instabilities are a typical feature of tokamaks. They don't happen in all confinement devices, and they are called disruptions. And these are conditions in which the pressure, this force of expansion of the plasma against the magnetic compression becomes unstable, and you can lose all the plasma energy in rather short times. So typically, the energy of the plasma contained in terms of temperature and density is lost in time scales of the order of a millisecond. So these are enormous power fluxes on the wall, but then the magnetic energy of the plasma, so the energy that is in the plasma because it carries a magnetic current, is also lost. This happens typically in time scales of several tens of milliseconds. When this happens, the plasma exerts on itself a very large electric field, and you can accelerate some of the electrons of the plasma to the speed of light. So you get something which is like one of the electron beams which are used for welding, but instead of having a current, I don't know, of some amps, you have a current of 10 megaamps. And you can imagine what an electron beam of 10 megaamps can do. It can really have serious damage to the wall of the reactor, and then you need to actually stop to repair. So this is something we want to avoid in ITER. And this is one of the main goals of some of our systems that we install in the machine to be sure that we operate in a stable domain, and that when these instabilities happen, we are able to get rid of the plasma energy in a smooth way, and it doesn't end up going in a localized area to the wall. Also, because the current decays very quickly, you get very large magnetic forces on the machine. So this is the phenomena that in tokamaks needs to be controlled most effectively to prevent damage to the components in the machine and melting of the wall. So ITER itself, the main components of ITER, as I said, is a tokamak. So it has this toroidal field, poloidal field, and central solenoid. Because the currents that we use are very large, they are millions of amperes, and we have to produce multi-Tesla fields. These coils are superconducting. So the field on the coils themselves, or the central solenoid or the toroidal field coils, is 11 to 13 Tesla. And they are made of a specific high field superconductor, which is niobium tin. Of course, they have to be cooled at very low temperatures of the order of 4K. The poloidal field coils produce lower fields of the order of 6 Tesla, and they are made of a simpler conductor. This is the one that is used typically for accelerators, which is niobium tin. The currents in these coils is very large, typically of the order of the plasma current. So if you have a coil, you have a plasma current of 15 megaamp, the typical current in the poloidal field coil is of the order of 10 megaamp. Actually, the divertor one, the one at the bottom, is more of the order of 20 megaamps. Then, of course, the plasma is enclosed in a vessel, which is what we call the vacuum vessel. And this vacuum vessel is protected by a set of elements that absorb the power from the plasma in terms of ions, but also in neutrons. This is what we call the blanket module. And the surface of this blanket module is coated by a material that can resist well the plasma interaction, which, as Dario said, we have changed recently to tungsten. And the bottom of the machine, which is called the divertor, is where we exhaust most of the power heat, but also the helium, the alpha particles. Once they are thermalized, we pump them through the bottom of the machine. And this is what is called the divertor. And there are cryopumps to absorb this helium. This is very important because helium is the ash of the fusion reactor. As if you don't exhaust it, it poisons the plasma, and basically you have no fuel more to burn. Because the coils are superconducting and they have to be at very low temperature, everything is enclosed in a very large thermoflask, which is what we call the cryostat. And because they have very different temperatures, there are what we call thermal seals, which are these green structures that are like thermal barriers. The large one is a thermal barrier from atmosphere to 4K, and these thermal shields, and then there's another one around the vacuum vessel to prevent the heat from the vacuum vessel and the plasma to get to the superconducting coils. And these are kept at minus 80 K, so minus 890 degrees C. Of course, the plasma here, you see very, very low temperatures, but in fact, the plasma in the center is typically at temperatures of 200 million C or larger. So you can see that within a space of the order of 2 meters, you go from a temperature which is more than 10 times the center of the sun, that of the center of the sun, to practically the lowest temperature in the universe. And this gives you an idea of how good the magnetic fields are as insulator, and also how complicated it is to cool the magnetic coils to this very low temperature when they are in these complicated conditions. Now, to heat up the plasma, as I said, we have 3 heating schemes. The This is the way they are displaced around the torus. So this is where the reactor is and the heating scheme. So we have neutral beam injectors, 33 megawatts, upgraded to 50. And we have electron heating and ion heating. So this resonate on the cyclotron frequency. So this is the product of the charge of the particle by the magnetic field divided by the mass. So for ions, because they are heavier in ITER, this is of the order of megahertz, which is typical radio frequency wave. And for electrons, this is much higher. This is of the order of gigahertz. And you can see, and I wanted to show it like that, this is what we are proposing to change. We are proposing to increase this amount of heating substantially. Before we were thinking of more than 20 to 40 megawatts. Now we are proposing to go up to 67, and we are keeping the ion heating, but we are removing one of the antennas. So these are changes that are not yet approved. That is why they are in dashed line. Everything which is in a dashed line here is not yet approved, and we will we seek for approval of these plans later next year, as I will explain. In addition to all these schemes and coils, and we have a lot of instruments to measure the plasma parameter. We have to measure the temperature, the composition, the density. There are many of the plasma properties that we have to measure, and for this we have 16 instruments that measure 100 parameters. They are inside the vessel, in ports around the vessel, and then we have a set of three-dimensional coils, and these are to control the plasma symmetry or to create a plasma asymmetry that we like. And this is what we call the correction of the error field, that these are to correct asymmetries we don't like, and then the Helm control coils, which are to create asymmetries that we like. The green coils are outside the vessel, they are superconducting coils, and the blue ones are inside the vessel, and they are copper coils. One of the objectives of ITER is to demonstrate the technology of fusion, and because of this, we want to demonstrate the production of tritium in the machine. ITER is going to use tritium from external sources, but for fusion reactor, the amount of tritium on Earth is not enough, and therefore you need to produce the tritium itself from lithium. And for this, one has to demonstrate that this is possible. This is what is done in what we call the test blanket systems in ITER. They are installed in 2 of the ports of the tokamak, and their mission is to demonstrate that actually the heat you extract from fusion and the neutrons you extract from fusion can provide both production of tritium from reaction with lithium, but also that they are good enough to produce electricity production, because you have to then get this heat into a turbine. Of course, in ITER we don't have a turbine, so we demonstrate the basis of the principle. And there are several concepts, 4 concepts that are going to be tested in ITER in the first phase. Now, ITER as a project, so this is the technical part. Now we go more to the project side, and also how we are going regarding the construction and the installation of these components. So the origin of this idea was a meeting of one country that doesn't exist, that was called the Soviet Union, which is all Russia and all the Russian Empire provinces, and the United States. And then there was an agreement to create, at that time, an international project to develop fusion energy. And this is the birth of ITER. As you can see, it was maybe when many of you were not born, or maybe your parents were born, I don't know, but it was a long time ago. Now, there was a series of design activities to conclude to a design of the machine. And so actually in 2000, at the end of 2005, the ITER members, which are China, EU, India, Japan, Korea, Russia, and the USA, agreed to build ITER and to build it in the site proposed by the European Union, which is in France, in the south of France. So the agreement was signed at the end of 2006, and the ITER project started at that time. The ITER members represent more than half of the world population and 85% of the gross domestic product. Now, the organization as such, because it took 1 year to ratify this agreement, started in October, and ITER is responsible to integrate the contributions from all the ITER members and to operate the facility. So at the organization, the ITER members are responsible, as I will show, to produce the ITER components, many of them, not all of them, but a large part of them. And the organization is responsible to integrate them, put them together, put them into operation, and then operate the facility, while the members are expected to contribute with people to the execution of the experimental program. So this is the composition of the ITER staff. So it's mostly European. If Europe should contribute with about 45% of the cost, while each ITER member contributes with 1/11 of it. And you can see that the proportion of staff is not in proportion to the cost, because this is one of the things we are trying to address, to increase the number of non-European staff in ITER. But it is difficult because, of course, to move countries from far away is complicated, etc. So you can see that even if theoretically there should be 45% of European, we are typically more of the 66%. Now, so that you have an idea of some of the components, so the thermoflask, which is what we call the ITER cryostat, it is actually the largest vacuum vessel ever built in the world. It actually provides isolation from ambient temperatures to low temperatures of the order of -100 to 200. So this vacuum has to provide this. It measures 30 by 30 meters, and it weighs about 4,000 tons, which is 1/3 of the weight of the Eiffel Tower. The magnets themselves have been now manufactured. These are all the magnets of ITER. The total weight you can see of these magnets is typically in the many hundreds of tons. The central solenoid is the largest individual one. It's made of 6 modules and it weighs 1,000 tons. To produce the superconductor of these magnets, particularly the niobium team, the worldwide production had to be increased by about an order of magnitude, which took some time, by the way, because you don't really, to create these magnets, you have to create the factory that produces the conductor. Then you have to produce the conductor. Then you have to produce the factory that produces the coil. So it has been a rather long process, but now this is completely finished, and all these coils are now at ITER. And the total mass of these coils is many, as you can see, many thousands of coils, of tons. Now the divertor, as you can see at the bottom, this is in pre-production. So we have several of these modules produced and qualified. This is where all the heat of the alpha particles and the external heat sends up, which is in ITER 150 megawatts of power. But this goes into rather small areas. So actually the heat flux on the surface of this component can be very high, about 1/2 of the power of the sun. And so that you can see here what this means in terms of power fluxes. The typical power flux of ITER is larger than the heat flux that you have a rocket when it comes back to Earth. It's not as large as the one of a rocket when it takes off, but it is of that order. So we are talking of significant heat fluxes that have to be sustained during hours. Now, because as I said, the ITER members are responsible to produce this, you can have an idea here who produces what. So you can see there are some components like the cryostat that has been produced by India. There are other components like the toroidal field coils where many people have contributed, most of the ITER members except India. There are others which are divided. And the idea of this division was that all the ITER members acquire technological knowledge to then build a fusion reactor by themselves if they want. So following ITER, there will be a prototype fusion reactor, but there is no obligation for the members of ITER to actually do this together. So in principle, the idea is that all what is learned from ITER is also shared with the members of ITER, and then they can use it for their own fusion program as they like. Because these components are built all over the world, they have to arrive in ITER. This is a bit complicated for the large components. They arrive by sea to a harbor near Marseille, and then they have to do about 100 kilometers. This is done during the night and in several days, by the way, because one has to cross the road. And you can see here from 2020 is when the components started to arrive. And now most of the large components, actually all the large components, have already arrived. And you can see here the arrival of toroidal field coils from various places, and the vacuum vessel and the central solenoid. The last big arrival was the upper colloidal field coil from Russia that happened earlier this year in February, I think it was. As I said, by now most of the large components of ITER are in place, except in terms of coils, half of the two-thirds of the vacuum vessel sectors are on the way. Now, ITER is not only a machine, it's a site. So the machine is built in this building that I am showing here with the pointer. This is where the components are assembled. And there are a large amount of infrastructure. So we actually have a 40 hectares plasma where the machine is. And we have electricity supply from the French high electricity network. We have transformer and rectifiers, cryo plants, etc. So it's a rather large, here you can see the towers for the exhaust of the heat. So it's a rather large, I would say, not only scientific, but industrial installation. This is seen from the top. So you can see here, for instance, for the 4 largest coils, which is this PF coil winding facility, the 4 largest coils cannot be transported by road. So actually, this is a factory. They build the coils. This is a European factory. The coils were built in situ. Also, the cryostat, the pieces can be made. They were made in India, but they cannot be transported together. And therefore, this cryostat workshop, which is an enormous building where the cryostats were welded and put together. Then we also have the cryogenic plant, which cools everything down, the coils down. And then we have what we call these magnet conversion buildings, which actually what they are enormous rectifiers, because of course we take altered current and we transform it in continuous current, into DC current. So these are large rectifier buildings. And then this is the tokamak building where the machine is where the reactor is located, and the assembly building is where the machine is assembled, and I will show how it looks. We also have other things, like this is the control room. So if you work in fusion and you eventually come to work to ITER, this is where you will be located when you run experiments, and this is what the control room will look like from the interior. So we said, I don't know if you have been in a fusion laboratory, but this is a typical what they look like. You have a part which is more the engineering side of the operation, which is on the right side here, and the physics side is on the left side, and we show different parameters which are of interest to the people that are running the experiment from the engineering and the physics side. And at the very corner, you can see here, this is a part which is dedicated to remote participation, because we expect a significant amount of people to be connected online when the ITER experiments run. And this is a connection directly into the control room. You can see it here. So this area here with the back screen is for remote participation, where the experimental team will discuss with external collaborators. This is a photo of the largest single unit plant in the world. And as you can see, the power, this is able to maintain 10,000 tons of metal, which are the superconducting coils, down to minus 269 degrees C. In installations like CERN, the total cooling power is larger than the one in ITER, but is distributed around many places. In the case of ITER, is in a single unit refrigerator, I would say. Now, I go quickly to machine assembly status. So this is a summary of what we have done in the last 3 years and the problems that we found at the end of last year. So the assembly of the tokamak itself is, as I said, is in a building. I saw it here at the back. This round thing is where the tokamak is located, and the machine is assembled from the top. So all the components, this is what it will look like when it is completely assembled. The tokamak on the left side is the tritium plant that produces the fuels for the reactor, and the right part is the diagnostic building where all the systems that measure plasma parameters are located. This is a very large building, which is actually based on seismic pillars, because it's a fusion reactor, it's a nuclear reactor, and it's a single piece unit so that it can move if there is an earthquake and there are no damages to the components installed inside. So we have several cranes and installation rigs where we pre-assemble the component, and then with these very big cranes, all the components are brought into the tokamak building from the top. So this is an example of the machine is divided into 9 sectors. So there is like the donut is divided into 9 slides. So this is one slide. It has one vacuum vessel sector that you can see here with 2 toroidal field coils. And then all together is transported with this crane. This weighs 1,000 tons and is displaced and located on the tokamak building, which is this. So the sector comes from the top and is installed here. And the parts, of course, are very large. They measure 12 to 15 meters. They weigh 1,000 tons, but still you have to locate them on these supports, and they have to be assembled with a very high precision and located with a very high precision. And the reason for this is that the magnetic field that you create has to be very symmetric. If the magnetic field that you create is not a perfect torus, it has like bumps, then the pressure that you can put inside the magnetic field is reduced. And because of this thing that you could think is an engineering feat is actually a bit more complicated, because there are some deviations of these components that make, depending on how they affect the stability of the plasma, they are important. And some of the deviations from the nominal position are not important. And typical alignment precisions are 1 millimeter. So you have components that weigh so much and you have to locate with 1 millimeter. One is to devise a way to identify which deviations from this ideal position are important and not important. And we have given guidelines to the engineering team how to do it. And this was demonstrated successful at the end of 2022. Took a while, but it worked. And what you have to do is you have to calculate what is the magnetic symmetry of the field that you want when the machine is operating. Then this means that the coils are at minus 269 degrees Celsius, and you have to, and not only that, but you also, the coils are energized, so there is very large magnetic forces among them. So what you do is you calculate that, and then you map back to room temperature position, and then you give the coordinates to the engineer to align. And because the expansion of these coils is very large, I mean, a few degrees of difference of temperature make the expansion is of the order of a millimeter. The temperature in all the assembly building of ITER is maintained to 22 degrees plus minus 2. So the machine is aligned at a given temperature, so that then you can do this mapping properly. And this is done through calculations of the response of the plasma by magnetohydrodynamic perturbation to the deviation of the magnetic field from symmetry. So it's not a pure geometrical alignment, it's actually quite complicated. It has a lot of physics in it, it's not just pure engineering. Now, what happened at the end of last year is that we found two things. One we knew and the other we didn't know. One was that there are some imperfections in the manufacturing of the vacuum vessel, but we thought we could solve them by welding by hand the facts that were affected. The vacuum vessel of ITER is considered legally like the vacuum vessel of a fission reactor. So the welding has to be qualified, and it's automatic, and it has a procedure to do it. And these inaccuracies don't allow you to do this, but they were in few places, and it was thought that this could be solved by requalifying the method for these places. But then later, what we also found is that this was a very unfortunate thing, was that the cooling pipes in these thermal seals that prevent the heat to go from the vacuum vessel to the superconducting coils actually had cracks. These seals are, you can see they are silver plated. This is all silver, and they have pipes of cooling where helium goes through these pipes. And because there was a wrong procedure in the cleaning of these pipes before they were welded, corrosion started and leaks started. And this is a very complicated thing, because this thermoflask where you have the coils would not have been in vacuum. This, of course, means that you may have a worse thermal transfer from the atmosphere, but also that you have a gas inside this cryostat. And when you change the currents in the magnetic field, you could create a plasma outside the tokamak. And this is something that you don't want to do, because then you have arcs between coils, etc. And because of this, it was decided to stop the construction of ITER and do the repairs. And you can find all the details in the ITER newslines. This is public. No, there is no secret here. So what we are doing now is to remove all these corroded pipes and repair them, and actually weld new ones, and where the corrosion is actually very large, to have a complete new thermal seal manufacture, and also to repair the vacuum vessel. And for this, we had to take the vacuum vessel out. So this is the sector. I show you the sector when it came in. This is when it went out. This was earlier this year. And this is now under repair. So we are disassembled this, and we are in repair. So because of this, now we have a situation in which before we were planning the ITER research plan and the operational plan was kind of limited by the hardware that we would have, not only from the core of the machine for the coils, but the heating system, the diagnostic system that would come after we had built the machine. But now we're in a situation which is the other way around. We are getting the systems to operate ITER, but we don't have the core of the tokamak. And because of this, we are actually doing what we call a new baseline. This was presented by the ITER director in October at the IEA Fusion Energy Conference. And what we are trying to do is to optimize the overall ITER plan, because we have, as I said, a different boundary condition. And this means that we have to do different things, but we also can do opportunities to do things better. In this area, one of the big decisions was to what do we do related to the first wall material of ITER, because the first wall material of ITER was chosen at the time to maximize the probability to get in high Q operation, because at that time there was no other better material. In the meantime, other material which is more promising for long-term fusion reaction has been explored, which is tungsten. Now it has been operating in several tokamaks over many years, at the substrate in Germany, west in France, and east in China. And this is the material which is being considered for fusion reactors. So one of the things we are actually proposing is to actually change material. This, of course, adds some risk that we have to compensate. And one of the reasons for this, one of the means that we have to compensate for this, is the change of the heating systems, which I proposed before. So this has been a very difficult decision, but it's been made. What we are trying to do at the moment is to install in the machine the mitigation schemes that will serve us to mitigate the risk of doing this change. So we have won on that side, one side, because tungsten is much more resilient to power loads. So the problems of disruptions, for instance, have become much less serious than before. But on the other hand, the contamination of tungsten with the plasma can radiate much more of the plasma energy, and you have a higher risk to get to the high temperatures that you need for fusion. And because of this, we are proposing a new way to do the research in ITER and the new equipment, mostly a change of the heating schemes to be more compatible with this choice, and also to put more heating so that we have a more robust approach to high Q operation, to Q equal 10 operation. This is what we call the new ITER baseline. We are going to divide the operation in DT in two phases. In one, which we go for the goal of fusion power production in Q equal 10, and then we go for the long pulse. And this is a plan that, as I said, has been presented for the first time to the public, let's say, in October, to our governing bodies also in November. And we have several objectives. It's a similar plan to what we had before, but with some specific features, like we start with the gas that we want to use in ITER in deuterium as soon as possible. The first campaign is more aggressive because we have much more equipment than we had before. Before, in the first campaign of ITER, we were planning to go to 1 megaamp. Now in the first campaign of ITER, we go to 15 megaamp. But of course, the amount of equipment that we have is 10 times higher than before. So we can do this. And then, as I said, in the second campaign, we concentrate in the achievement of the 300 to 500 second goal with a relatively low integrated neutron fluence to prevent the activation, a very large activation of components, and then we will go to the second phase. And this is what we call is the new baseline. Where we are with this is we have presented the scientific basis for the plan to our scientific and technical committee and to our governing body, and this was last week. We got a good, I would say, a good overall evaluation, and the plan is to present the final proposal, and this is something that will include the schedule and the cost. This is something we have not presented so far. We have presented the technical part in June this year. So with this, I arrive at my conclusion. So ITER will demonstrate, as I said, the science and the technology of fusion as an energy source. We have done a lot of progress in 2020, I have to say. It was a bit challenging because we have the COVID. Now the problem is that we found some challenges at the end of the year, and we have to identify. And because of this, we are doing new plans. And the goal of these new plans is to minimize the impact of the assembly is delayed, taking advantage that we have more available systems, but the delay of the machine is there, and we try to minimize the impact of this. And I said take advantage of the opportunities because we have more systems, and to maintain the old plan doesn't make any sense. And we are also minimizing risk to high Q operation. For instance, the change of tungsten. In the first phase, we are considering not having water cooling in the first wall, so we have disruption, we don't have a water cooling, etc. And then as a goal, of course, the goal of ITER remains the same, independent of the plan. We have to address key issues for a reactor, technologies and physics, particularly the issue of self-heated plasmas, what happens to a gas when it is dominated by fusion, how we integrate high fusion production with acceptable wall fluxes, and how we control these plasmas. In particular, how we avoid the plasmas become unstable and disrupt. And of course, the technology, we have to develop how we put the tritium in, how we get it out, how we clean it, how we produce tritium, how we heat the plasma, how we control, and how we build the plasma phasing components that sustain these very strong power fluxes. Thank you very much.
Alberto, thank you very much for this very comprehensive presentation about ITER, showing all the challenges also, like I mentioned before in the JT60 presentation, also with the assembly challenges of ITER, which are really something. And also with explaining so clearly what is the current status of ITER and the direction of the project, because since ITER is a very widespread project, there is always a lot of rumors, some of them true, some of them not, so it's always a little bit of confusion for where ITER is going. So it's always useful to hear from you, person who is actually working there, how is the real
there are many rumors. The issue, I think, at the what happened to be open in the last year is that when these problems were identified, it was quite clear that we had to do a big change of plans. Because if we continue, we could not keep the plan as it was because the delays were significant, and also because they did not make any sense, because the plans were done, as I said, with some boundary conditions. In the old plans, what was driving the plan was the availability of system, not the machine. The machine was supposed to be available, and it was the system that came, one heating system 1 year and the next diagnostic the other year, etc. And now we are in the inverse solution. We have the systems, but we don't have the core of the tokamak. So we couldn't keep the plan. And of course, this is a major rearrangement of the plan, because this is a main deviation of the plan of ITER since 2000. I mean, we have a plan from 2016. It was a revision of the plan that we have in 2008. So this one is really a major change. So it has taken a long while to come there, because one has to then do all the analysis and to be sure that the plan is solid, because you can just not invent things. So there are a lot of calculations, discussions with the presence in the experiments, if the assumptions that we are taking are correct. So, and this has, of course, this kind of the fact that there was a new plan in development, but that the details were not known, have led to a lot of rumorology. I think now we are out of this, by the way. But it is true that, let's say, for the first half of this year and maybe the end of the year, there have been many things going on, many rumors going on. But I think this is unavoidable.
Yeah, that is true. That is true. At least for the science community and for the students working in fusion, it's always good to have things clear. So thank you so much for this. The floor is, of course, open for questions here by chat or by raising your hand. So I see the first question here on the chat. So from Nico Good.
So ITER is supposed to demonstrate tritium breeding. This is correct. We are supposed to demonstrate tritium breeding, but only we are to demonstrate tritium breeding, but not tritium self-sustainment. So what we in order to do that, you need a demo reactor, because you have to put these modules that we are testing in 2 ports. All the protection of the inner wall has to be done with this module. And actually, since we don't know how to design these modules, because this is what we are testing in ITER, you cannot do the next step. So ITER will only demonstrate the first step. Once we have demonstrated that, then it should work in a reactor. But this is actually one of the objectives in ITER. So it's very difficult to decide. I mean, as I said, we are actually testing 4 different concepts. And that is why we are testing the concept. And for a reactor, you have to actually use the best one. So you cannot install maybe I explain better with the slide, because this, one moment. In a reactor, what we do in ITER is two of these ports, which are here, are equipped with one of these modules. There are 4 modules. You can see maybe for green, there are some green.
We cannot see your screen.
Sorry, I thought I had shared. No, I forgot to click, sorry. No, I thought I had shared.
Yes, now
so
we can.
if you look here, sorry, if you look here, one moment, I clicked. When do I? Okay, laser pointer. Sorry. If you see here, there are 4 like green straps. So these are 4 concepts that we are testing in ITER. And this is, by the way, the plant that circulates the lithium and the coolant, and then refines the tritium that you extract. So you see, it's not small installation for these 4 modules. But in a reactor, what you need to do is all these yellow things which are here should be of this type. So in ITER, what we are using is 2 of these ports at the equatorial level, the gray ports, to test 4 concepts. Then in a reactor, the best one is what should populate all the inner walls. So that is why in ITER, since we don't know which is the best one, we can actually not do the tritium breeding at the scale. Because for a reactor to work, you have to have all of them made that they can produce tritium. In ITER, these yellow blanket modules are just steel and water, so they stop the neutron and they extract the heat. By the way, we don't convert the heat to electricity either. So ITER is a proof of principle. The part of a reactor, they say, in terms of producing electricity, is not part of the mission. So I don't know if there are.
Okay. Thank you very much. I think there is another question.
Okay.
In the chat.
Okay, so yes, there is. We have 2 ways to control edge instabilities, and one moment, I display again, and indeed, ITER has a resonant magnetic perturbations, and these are, one moment, these blue coils here. You see here there are these blue rectangles. There are 27, and they are used to create resonant magnetic perturbations to perturb the plasma, produce this instability. By the way, this is produced with Jorek, who is from Professor Guido Huysmans from Eindhoven. And indeed, we plan to use them precisely for this. By the way, this is the best Helm control system that exists in the world. There is no machine that has anything like this, ever. So it's actually very flexible, because we don't know how we are going to use it, so we have to have flexibility.
Okay, thank you very much,
Okay.
Alberto. I think there are no more questions, just a comment of appreciation in the chat for the very nice thread of joining engineering and planning in a project. So Alberto, thank you very much for joining us again. We're happy to have you here, and then hopefully count on you for future events as well.
Okay, good. Okay.
Good luck with the ITER planning.
Okay, thank you very much. Thank you.
Thank you so much.
Bye.
Bye. So, well, to all the attendees, we have come to the conclusion of the event. Thank you so much for joining another edition of the FuseNet Master event. And of course, a warm welcome to all the new students who are joining this event for the first time. We hope that this event managed to not only show you the different activities of FuseNet and the ways that you can benefit from the FuseNet budget and activities that we propose for you, but also that it could give you an overview of the different paths and fields that are involved in fusion research, and that you can access already from your master thesis and your master projects, but also that if you pursue a career in fusion, the different options that you have in the different research centers, companies, institutions. So this is the main goal of the event, as well as to put you in touch with your fellow students from different master courses, and see that there is a very strong interest in fusion among the community of young students, which we wish to keep going, because as you have seen in all the presentations, the timeline for fusion requires young people working on it from the very early stages of education. So everybody's counting on you. We all are. So yeah, thank you so much for being part of this event. Also, thank you so much to my team here. I see Mira. Thank you so much for joining. you will see that when you write to the executive office of FuseNet, it's either Mira or myself answering to you. So it's also good for us that you know who is running the event. Also behind the scenes, Bjorn and David, which are our student assistants that run all the help us running with the activities of FuseNet. If you anything related to IT, we have Bjorn. The content manager is David, so you will see him in the newsletter. That's who he signs. And yeah, we wish you the best of your career. We hope that you stay involved within FuseNet, within our initiatives. And we are always happy to collaborate and to talk to you to whatever inquiries you may have about Fusion and to promote Fusion education. So thank you so much.